Our third theme comes from the University of Mittweida, and they are solving the challenge number 2022, a drone with suitable sensor technology on board that could monitor the water quality of surface waters so that hazards can be detected in time. The enterprise that proposed it was Endress and Hausser.
An essential element of life, towns are built around it to ensure survival, public health, and all safety. We are so used to having access to safe water 24 hours a day, 7 days a week. But do we even know its true value? We are not the only ones living. Our whole ecosystem is built around it. Organisms find a habitat for water. If we don't care about our water, we risk our survival and leave a world in which water organisms are non-existent and ecosystems are dry land.
That's precisely why we are standing here today. We want to protect our water, and we think you do too. In the future, we won't be able to do this by going out on the boat, taking samples, having them analyzed in the laboratory, and just then drawing our conclusions from that. That takes way too long. Until then, the exactly described scenario will happen. That's why we need an innovative solution to speed this whole process up. We need something that allows us to draw our conclusions about the water quality in real time. That's exactly where our challenge comes in. It challenges us to develop a solution that allows us to draw our conclusions in real time without sampling in order to detect hazards in time. In addition to that, we have to store the measurements and allow the user to access them at any time. However, that's not all.
But who are we? We are two computer scientists, me, Paul, and Nicole, and two mechanics, Johann and Zekeriya. Our mentor, Professor Langer, completes the team with his expertise in connectivity service and automotive software. But back to the topic. To achieve this, we went outside into the nature. But why did we go into the nature? Very simple. Because every technology that's good are inspired by nature. So we are inspired too. We met Pascal the pond skater. He is nearly flying over the surface from the water, and he has no problem for him to fly from one point to the other within a few seconds. Sorry. But even he is not really up to the challenge. So he can't tell us the parameters of the water, and also he is not speaking our language to tell us. However, we took him as inspiration.
That's exactly how our first prototype was created. You can see it has a great similarity to Pascal. It has the legs that enable the drone to land on the water. And we also planned to put a sensor at the bottom of the drone to measure the water parameters. We put this prototype into practice and tested it. See for yourself how this test looked like. Oh, sorry, of course, it wasn't that bad. Nevertheless, with this, we could not solve the challenge. Due to the additional weight at the top and at the bottom of the drone, the drone wasn't able to find its center of gravity. At first, it wanted to balance the weight into one direction, but then directly into another. This ultimately led to the drone crash. But don't worry, the drone is fine.
The drone is still fine, but it has brought us nothing. That's it, we failed. But we don't give up. It has become much bigger than we would have thought. Much bigger than Pascal, and also much bigger than our prototype. But I have good news for you. It still works on the same principle and led us to our goal. To achieve this, we divided our team into a mechanical and technical area. For example, Johann and Zekeriya constructed and printed the additional parts. Me, the team leader, and Nicole, our co-leader, managed the data transmission, data storage, and data representation. So every week we met as a team to discuss our current status and the future development steps. Several times a week we met individually in the IT and technical team and mechanical team.
So what's the outcome? We have our drone. This drone lands on the water, unfolds the sensor and measures the water parameters. These data gets transmitted to a microcontroller that is attached to the drone. This microcontroller sends the data to another microcontroller that is located on land. And this one stores the data into a database, which is then accessed by a web application to show the measurements of the water in real time to the user. That's it. A very simple solution, but with great impact and future potential.
But of course, there's more to it than that. Let's use Pascal again to help us. Now he is the one who uses our system to measure the quality of his home pond. Of course, the obvious adding part are the two floating bodies. They are self-calculated, constructed, printing, and added to the drone, all thanks to Zekeriya and Johann. They got their inspiration from Pascal, but also from a water blade. The next thing is the device that folds the sensor in and out. Let's call it flap. The flap is also self-calculated, constructed, designed, and adapted to the drone. With this flap, the sensor is extended at the right moment to perform a measurement and reattracted again to provide more protection during the flight. The next thing is the device that is attached to the drone. You can see it here. In this thing, it is also self-calculated, printed, 3D printed, and calculated, and bring it to the drone. In this case, all the components have enough space and water protection they need.
These components are, for example, the sensor that measures the water parameters, but also an T-beam ESP32. That's the microcontroller that supplies itself with the needed energy that is attached to the drone, and it also enables all the functionality of our system. So, for example, it controls a little motor that is also inside of this attached box to drive our flap. But not only that, it also transfers the data to our microcontroller that is located on that.
We transfer our data via Bluetooth. No, of course not. But I think everybody of you knows Bluetooth. Instead of Bluetooth, we use LoRa. It's the same principle and the same goal. But instead of this, LoRa is an extremely power-saving and long-range data transmission technology. Therefore, LoRa enables us the required communication between the two microcontrollers. In addition to that, the one ESP32, which receives the measurement results, sends them to a database. This database stores the measurement results and allows our web application, which we created, to display them to the user. With this developed web application, it is very easy to carry out a measurement here in Spain and be informed or alerted about it back in Germany.
But our development doesn't stop here. What we created until now is just the basis for our further development. Together with Endress Hausser, the company that gave us this challenge, we want to continue our journey. We dream of adapting our design system to any suitable drone. And that is no problem, because all you need to do is to adapt the 3D printed parts to this specific drone. Anything else will work exactly the same. In addition to that, we want to develop an automated system. And that's also no problem, because DJI, that is the constructor of this drone, is actually already offering software that helps you with the implementation of such automated system. So it's no science fiction. But let me explain to you how we want, or how we think about this automated system. For this, please imagine that you are the one that wants to measure the water parameters in order to detect the hazards in time. To achieve this, you only have to sit in front of your PC, open our web application, and then specify the measuring points on a map that is inside of the web application. Then all you need to do to start this whole measuring process is to press a button on the drone. After that, the drone will automatically fly to the specified points, will land on the water, will unfold the sensor, will carry out the measurement, and will send it back to the database. This database is again accessed by our web application. This allows you to look at the data or at the measurements in real time. And the best part of it is if a measurement is detected that is not within the natural range, then you will be alerted immediately, and that without any effort. And that is vital, because water is an essential element of life, but it hasn't constant existence. However, our population is growing. If we now choose to ignore the protection of our water, we will have a growing population and the available water becoming less and less. We cannot continue like this. Without our innovation, anything else will become irrelevant, because at a certain point, we will simply no longer exist. We need water after 2 to 3 days, otherwise our survival isn't guaranteed. In addition to that, a 2018 edition of the United Nations World Water Development Report stated that nearly 6 billion people will suffer from clean water scarcity by 2050. And our system is designed to prevent this. And to prove to you that this really works, we would like to demonstrate it to you. What I would really like to say to you now is, please keep calm on your seats, don't make any hasty movements, please don't run out of the room either. But I can't, because we can't start a drone in this small room. It's too big and it's for our own safety. But we came prepared. So just keep calm on your seats and enjoy our show, even if it's smaller. Thank you for your attention.
Thank you very much for your presentation. Professor Nabil Asadi is going to make his question.
Thank you. Have you conducted any field tests, validation studies to assess the accuracy and performance of your drone system in monitoring water quality? What were the results, and how do they support the effectiveness of your system in detecting potential hazards?
So you mean if we tested it in different weather conditions or drone?
If you have, if you've done a test of weather and you have results of the quality of the weather.
We tested it in different conditions. So, for example, when it's raining, you have to, of course, you have to look outside if it's raining heavily, because then maybe the drone, if it's too windy, will crash eventually. But with this drone that we have here, it's really stable. So weather conditions are not the problem, and also the sensor. It doesn't care about weather. I would say.
I ask about the reality of the results of the.
Yeah. Okay. we tested in different weather conditions and we didn't find a difference in the measurements.
So with the sensor you can measure pH, temperature, and the soft edge oxygen. So you can look at the results and then you have results what's the hazard or if it's a hazard but we can't test it.
You have a traditional measurement,
Yeah.
and you compare between the.
Yeah. So if the pH value is higher or lower than that, and yeah, that's our result.
Thank you so much.
Thank you very much. Professor Tawada, you have the word.
Thank you. So I go for the money again. So how much money did you spend to build the different parts all together? Because you said that you designed the different parts by yourself, like 3D printing, and then part of it is bought, I guess. So.
No, it's not bought, it's printed.
But everything.
I think you mean.
But part of it is from a company, isn't it?
Yeah.
The big
So-
part is for a company. When
Yes.
floating bodies, this one, and all the stuff, this is printed by ourselves, and the other one is from DJI. So it's
Okay,
a
so
standard
more or
drone
less
you can buy.
money of the parts that you have built, so how much have you spent, and then the thing that you bought, like to have an idea of how much it was.
So to print everything in the prototype, I think it was around 700, 800 euros.
Okay.
But the most of the money goes for the filament, so the material to print this.
Maybe one thing to add, the drone is really expensive, but
Yeah.
we didn't bought it. We rented it for the time period that we have to develop this prototype. So it isn't bought, but we used the whole budget to create this and to test with several prototypes.
So it's rented. Okay.
Yeah.
Okay.
Yes.
Yes, thank you.
Professor Parsenavelos, you have.
Yes, I would ask you what crazy professor would lend you the M300, which costs like 12 to 15,000 euros, and the renting was a good choice. I mean, I wouldn't give you my drones to play in the water. So my question is, and I didn't see it in the video, because I liked your first implementation, which was your drone. I liked it a lot. And but it was self-explainable that if you have moving parts in a drone, it's not gonna stabilize and it's gonna possibly crash as it did. So you can use the mentors of the EURECA-Pro before you do some testings to help you in these things before you spend money on that. But also this has the same exact problem, and by touching the sea, touching the water, I think there is a big possibility that it's not going to turn off and it's not going to stabilize. And so did you do many tests in the moving lake to see that result? Because I didn't see in the video, it was cut in that exact moment that I wanted to see.
Okay.
Yeah, our step was without the drone, with only a little weight, then with the drone, but without the accus. Then with the accus, so we tested step by step to make sure that the drone is not going to the sea. So yeah, that's what we.
It turned off in the sea?
Yeah, that's what you see. That's what was our last step. So,
Okay. Thank
Yeah.
you.
No, my question is about water quality. What parameters are you measuring with the sensor?
Yeah, as I said, pH value you can
Just
measure,
pH?
the temperature, and the soft oxygen.
Okay.
That's true.
Just basic parameters.
Yeah.
And have you considered multispectral and hyperspectral drones? Of course, you've done that.
Yeah, you can.
You can do that also?
Yeah.
Okay,
So we have to choose another sensor, or maybe more sensors, but I think that's not a problem. We have to extend our printing.
Okay, so thank you very much for your presentation.